And we're back. I'm Mr. Steele, and I'm once again here to go through one of the questions from the Essential Skills quiz that you're going to be taking in the first half of Honors Pre-Cal. In this video, I'm going to attack the section of the ESQ model focused on question number 6. So, in a sense, I guess I'm attacking question number 6 on the ESQ model for Honors Pre-Calculus that's focused on right triangles and sort of all the skills related to them across the 4 problems in this section of your model. We cover basically all the big essential ideas of right triangles, including trigonometry, special right triangles, and just the Pythagorean theorem itself. So in this video, I'm going to talk through each of those ideas, give you the brief overview to kind of jog your memory if that's what you're looking for, and then I'll go question by question or problem by problem, however you want to think about it, and demonstrate how those skills get applied in the questions you're going to see on the ESQ model this quarter. So without further ado, I'm not going to talk around it. I'm not going to beat around the bush. I'm just going to dive right in. Speaking of diving right in, there are 3 real key ideas that I would anticipate popping up in this section that I think would be helpful to kind of overview and kind of get into your head before you dive in. If you're just trying to jog your memory, I think this section will be a really helpful place to kind of get the big ideas back into your mind. So the first of those ideas is what sort of brings together this entire section, which is all about right triangles, and that would be just using what we call the special right triangles. These special right triangles have angle relationships that create really nice clean ratios between the 3 sides, as well as clean angles themselves. Obviously there are an infinite number of right triangles that are out there, but these are the ones where everything is sort of nice overall. So what those 2 right triangles are, and there are 2 of them. I'll start with the cleaner of the 2, and I guess that's subjective a little bit, but I mean cleaner just because it's a very simple relationship between the 3 pieces, and that is what's known as the isosceles right triangle, and that one has angles of 45 degrees as the 2 acute angles. So judging by the fact that those 2 angles are acute but also equivalent to one another, the equivalency makes this an isosceles right triangle, which means these 2 sides are going to be congruent. But of course it's a right triangle, so the only way for that to be possible is to have those 2 base angles be equal to 45 degrees. Now when this happens, there are pretty straightforward ratios between all the 3 sides. Basically you probably know this as 1, 1, root 2, but there are other versions that are out there. Sometimes you'll see this instead as root 2, and 2. Or if you wanted to kind of have one that just sort of encompasses everything itself, I think x, and x root 2 does that pretty well. But for simplicity, I'm going to go back with the kind of classic ratio that's out there. Since we're going to get to show you what this looks like, I typically have seen this one written myself as 1, 1, root 2. So in other words, what that's describing is the ratio between the 2 sides, or the 3 sides. In other words, this side and this side, the ones that are adjacent to the right angle, are going to be exactly the same value each time. And then the hypotenuse, which is opposite the right angle, is going to be root 2 times whatever those other 2 sides are. And we can use those relationships, that proportionality, to figure out what the side lengths are for any isosceles right triangle, no matter how big any of the sides are. So now that's the first one, but there's a second one. Let's see if I can draw this effectively. So here's my rendition of the second one here. Again, it's right triangle. In this case, there's going to be a 60-degree base angle, or opposite a 30-degree angle. And when that happens, it creates yet once again another special right triangle. In this particular case, opposite the 30-degree angle is the shortest side, so that typically has a value of 1. Opposite the 60-degree angle would be root 3 times that, and then the hypotenuse is double the shortest side. So this is the most typical arrangement that you'll see for the side lengths in order to set up the proportionality. You could think about this instead as x, x root 3, and 2x if you so desired. That captures the idea that whatever that short side is, the other 2's proportions there. But like I did earlier, I'm just going to go with the classic version. This is typically 1, root 3, and 2. And I will point out to you that root 3 is about 1.7, so 2 is bigger than it, which matches up with what we're supposed to have, which is the largest angle is supposed to be opposite the largest side, and the hypotenuse is always supposed to be the longest side. This actually does work out that way. So those are the two that we're going to use. I think 2 of the 4 problems that are given on this ESQ model feature these special right triangles, like 1 apiece. So I'll show you how to actually use that proportionality in the video for those respective questions. The second thing we want to address is trig ratios. Basically, there are 6 trigonometric ratios out there, but for us, we're going to be focused on basic trig, and we're going to use that basic trigonometry to establish the relationships between the sides and the angles. Specifically, if we have a right triangle, I'm just going to go ahead and establish this right triangle here. I'm going to say that we have an angle theta and that our sides are A, B, and C. Then there are 3 trigonometric ratios that are automatically established here. Again, there are 6, but I'm just going to stay with the basic 3 that your calculators tend to have. First, we're going to have sine of theta. Sine of theta is going to be the opposite side divided by the hypotenuse, which, looking at our particular triangle here, opposite the angle theta will be A, and the hypotenuse will be C. The second of those ratios is going to be cosine of theta, which is going to be the adjacent side over the hypotenuse. So once again, using our given triangle here, the adjacent side is going to be B, and the hypotenuse will be C. Last but not least, we have tangent. Tangent of theta is a ratio that's often associated with slope in the future, and here it sort of is as well. It does provide you the slope of the hypotenuse if there's some systems in place, but for this, the important part is that we get that tangent is opposite over adjacent, and with the angle theta established, opposite is A, and adjacent is B. So those are the 3 ratios we'll use. We will actually be defining and answering this question sometimes in terms of tangent, cosine, or sine. Just depends on how the problem is provided to us, and I think it's the 3rd one on this section has that. I'll show you how that works when we get to that question. Last but not least, I'll draw one more triangle here. Actually, I'll just make it kind of a little bit different here. I'll use theta one more time, but I'll do x, y, and r as our side lengths. In this case, the Pythagorean theorem establishes the connection between the side lengths themselves. No angle required here, just the connection between the side lengths, although of course the angles are affected as well. But as you know it, you probably know it as a squared plus b squared equals c squared. I'm going to write this one as x squared plus y squared equals r squared. So the sum of the 2 shorter sides, the 2 legs, squares, is going to be equal to the square of the hypotenuse. And this relationship holds, and it allows us to connect some things together when we're given 2 sides of the triangle. So with that said, that covers all the big ideas for the right triangle work we're going to do here. So let's go ahead and dive in and see how it plays out in problems. The first of the 4 problems in this section, or covering this question on your ESQ model, addresses a particular right triangle. In this case, we're given 1 side length and 1 of the base angles. And in this case, the base angle provided is 60 degrees. Being that this is a right angle, that forces us to automatically have a 30-degree angle on the opposite side, which means we have a 30, 60, 90 right triangle. And that's helpful because that establishes a certain proportionality between all the side lengths, as I addressed in the key ideas section. So just so we have it sort of established here, I'll mirror this around, but the idea is the same. If we have 60 degrees and 30 degrees as our angles, and the right angle obviously on the other side, since this triangle does have to have all its angles add up to 180, the side lengths or ratios will be 1, root 3, and 2, opposite the 30 degrees, 60 degrees, and right angles respectively. So the way we're going to use that, and I'll use the triangle that's provided here to show it off, is I'm going to establish those lengths, the sort of proportional length or the unit length. I always want to call them unit length because it's sort of the base unit of a 30, 60, 90 right triangle. And I'm going to go ahead and write those inside the triangle. So opposite 30 degrees will be the 1, opposite 60 degrees will be the root 3, and opposite the right angle, aka the hypotenuse, will be 2. Now with these in place, what I'm going to do is I'm going to set up proportions. I'm going to set up equations of 2 ratios, and then I'll just solve those equations for the missing variable. So here's what I mean, and I'll use a different color for each one. So first, we have this relationship, 12 over root 3. So basically, I'm going to start there. One of our 2 proportions, one of our 2 equations, will start with outside over inside, 12 over root 3, is equal to, and then I'm going to look at the rest of the triangle. Well, let's solve for x first. That's going to have to be equal to x over 2. So again, outside over inside. Now from here you can kind of see what happens. From here we're going to solve for x. So I'm going to multiply both sides. I'll use pink for that. We're going to multiply both sides by 2. That's going to give me 24 over root 3. is equal to x, and that is an acceptable answer as far as I have. I would always accept that answer since rationalizing isn't required in most pre-calculus classes. But if you preferred to make this sort of in its best form or to clean it up just a little bit, you could take this and do what's called a rationalizing. And rationalizing is sort of a relic of when people had to use an abacus in order to make some intense calculations. Dividing by a radical an irrational number is difficult, so they would instead do this. They'd multiply up and down by root 3, so that we're not changing the value at all, we're just cosmetically altering it. That would give us 24 root 3 divided by 3, and of course 24 over 3 is 8, which means this is equivalent to 8 root 3. So it's sort of your call which value or which version you want to write it with. I'll put both of them up here. Wasn't my finest boxing ever. Understatement of the year. There we go. Let's make that look a little bit better. There we go. So there's our stuff. So that's our first side length. Again, we use proportions in order to get there. For the second one, we've still got one side left to solve. I'm going to do the same thing. I mean, we do know x now, so I suppose we could use that, but I'm just going to go back to the original relationship here. So 12 over root 3 will be our first portion here. That gets us outside over inside using the given information and proportionality, and that's going to be equal to the bottom section, which outside over inside gives us 12 over root 3 equals y over 1. Now you can tell y over 1 is just equal to y, so why go too far here? One of our versions of the answer here will be 12 over root 3. That is correct. Again, there's nothing wrong with that answer. But if we want to rationalize this just to clean it up a little bit, maybe you already see it a little bit, but I'm going to take that, oops, let's write it this way. I jumped ahead of myself. I'm going to take 12 over root 3 and multiply up and down by root 3. So that way I'm just changing the appearance, not the actual value. We'll get 12 root 3 divided by 3, which you can surely see is 4 root 3. And by the way, since this was 30, 60, 90, this should be half of the hypotenuse, so it actually adds up with what we had. But that's sort of not the point. It's illustrating how to use this proportionality technique. There it is. I still made that issue. I'm still having issues boxing this thing. Well, that's why I don't enjoy being in the ring. Not a boxer. But there's our other value. So again, our strategy here is to know this relationship. This is sort of the essential info here. You have to know that proportional relationship in order to set this up. But once you've had it, you can set up two quick proportions or just use it in your head. Like you can get there pretty quickly, I think, as well. And quickly figure out what those other two opposite sides are. So we've done it. So good job. We've got our first special right triangle out of the way. Didn't take any special efforts, but we did get the right answers. The next question we're going to attack is the second one. This one features a special right triangle as well. And by the way, it doesn't look like it's drawn to scale. I wouldn't ever assume that any picture is drawn to scale in that way. But we have what looks like a 45-degree angle inside a right triangle, which of course, as you might know, forces this other one to be 45 degrees so that all three angles add up to 180. Therefore, we have an isosceles right triangle, which establishes the proportionality or the proportions of the sides automatically for us. So if this is 45 degrees, as we talked about in the key ideas section, these two sides are congruent, and then of course the hypotenuse will be root 2 times their length. So given this setup, I'm going to use the exact same approach that I did on number 1, like the 30, 60, 90 right triangle, but this time I'm going to use the new proportions, 1, 1, and root 2. So I'll pop them in right here. So 1, 1, and root 2 are all in place, but here's the spot where we want to be. We can be a little clever. Notice that x is over 1 and so is y. So basically x and y are both going to be equal to the same thing. That's sort of the advantage of the setup. So we don't actually have to solve this problem twice or solve two proportions. We can just solve it once. So in a sense, when we go to set this up, and we will do it the same way we did last time, we'll set up a proportion with the side we were given, which was 18 over root 2. If we do outside over inside, a good recommendation. Then from here, I'm just going to go ahead and solve for x, but of course I'm also solving for y. It's kind of like, well, we get one for free. They're the same thing, so here we go. So again, outside over inside. Well, I mean, good news, everyone. We get x over 1, which is just equal to x, which means our answer can be expressed as 18 over root 2. But of course, as we did on the previous one, we can also rationalize that just so it looks a little bit cleaner. Again, not a requirement in every class, but again, consult your doctor, consult your teacher just to kind of check to see. We're going to get 18 root 2 over 2, which simplifies pretty clearly to 9 root 2. So in other words, x is equal to 9 root 2, and y is equal to the exact same thing because they are congruent to one another. So I'm just going to write the exact same thing, and then I'll box them both at the same time. So although we did have to do those two proportions on the 30, 60, 90 right triangle because they were different ratios, no such requirement here for a 45, 45. It's isosceles. Those two side lengths or the two legs are exactly the same length. So if you found one, you find the other for free. So a nice little tip. I will say sometimes this problem, they might not give you the hypotenuse. They might give you one leg. Well, in that case, use the fact that the two legs are equal to just quickly get the other leg, and then, of course, set up the proportion with the hypotenuse. You can get through it pretty quickly. The third of the problems throws us for a loop a little bit, or just throws us a little bit of a curveball. It's not a big looping 12-6 curveball for those of you who are baseball fans, but you know it's a curveball all the same. Like, you're gonna have to track this pitch out of the hand, which is to say this one doesn't have a special right triangle relationship. The reason I can tell is that this has 38 degrees, and in addition to being pretty cold when measured in Fahrenheit, 38 degrees is neither 30, 60, nor 45. So this is not going to be one of our special triangles, so we're not going to be able to quickly set it up by knowing the relationships between the sides or those proportions ahead of time. Instead, we're just going to have to use trigonometry. Our only possibility here is to use trig. So basically we need to use sine, cosine, and tangent, although again there are lots of different ways to set this up. I'm going to try to use the basic relationships and keep it as clean as possible, just sort of my goal. So looking in here, we are given the angle 38 degrees as one of our base angles, so I'm going to try to establish that as my relationship here. Again, if you wanted to, you could go up here and you could say this is 52 degrees and set it up from a different perspective. I'm just not going to go that route. I'm going to just stick with the 38 degrees for simplicity, so that way there's a uniform answer that we get for each of these. And I would recommend you do the same thing, just because you could potentially do some arithmetic mistakes when you go to set it up, so just be careful. So in this case, we got two sides defined, x and y. So I'm going to try to establish the relationship between the angle and first the side x. So looking on here, I've got the side x, and I have the angle 38. I want to set up a ratio, and my candidates are sine of theta, and actually I'll use theta here for simplicity, cosine of theta, and tangent of theta. And in fact, you know what the heck, while we're here, let's just evaluate what each of those are in terms of our picture. Let's just see which ones that we should use then. So looking at our first piece, sine is opposite over hypotenuse. That's going to be x over y. And I'll tell you right now, this one is not going to be our good choice, simply because we don't know either x or y. So basically that's not going to be our one to choose. We'll ignore that. We need at least one numeric value for us to be able to establish the relationship. Having said that, we can evaluate cosine. Cosine will be adjacent over hypotenuse, and this is going to give us the ability to solve for y. So let's do that one first. So based on this, we have the cosine of 38 degrees is equal to 5 over y. Now we need to solve for y, so there's a couple different ways to do this, but I'm going to attack it using the strategy most of my students did last year in Accelerated. I'm going to multiply both sides by y. The reason why is it's going to divide out the y on the right side. We're going to get y cosine of 38 degrees equals 5, and now I'm going to divide both sides by cosine of 38 degrees. When I do that, I'm going to get an expression that looks sort of crunchy, like there's no argument here, but our value is 5 divided by the cosine of 38 degrees. And if you were allowed a scientific or graphing calculator on this section, you could simplify that, but as far as I can tell, you're not. So basically, I'm not going to go that route. I'm just going to leave this in the most simplified form here. If you did need to use a graphing or a calculator, then of course you could finish that further. As a heads up too, if you do know some advanced trig, you might know already that this is equal to 5 secant of 38 degrees, but I don't believe in the first half of honors pre-cal you're expected to know the reciprocal trig ratios, so just know that that's a possibility, but that may not be something that you actually are aware of just yet. I'll just leave it up there just in case. So good job on us. We were able to evaluate and find the value of y, using cosine, and I'm betting tangent's going to be helpful in a similar way. So tangent is going to be opposite over adjacent, and relative to 38 degrees, opposite is x and adjacent is 5. So opposite and adjacent. Well, this one actually works out, I think, even better than the first one. This says that tangent of 38 degrees is going to equal x over 5. We need to solve for x, so okay. Let's multiply both sides by 5. Although it says stand 38 degrees, that's not what we're going for. But basically, this one's already done then. X is equal to 5 tangent of 38 degrees. So in this case, one of them turned out to come through pretty clean. It just kind of depends on which ratios you have and which one angle you're given. But in this case, we're able to find our two expressions. And again, I'm settling for the exact version just because it doesn't tell me to round to a particular value in this particular case. But again, if your teacher instructs you to approximate this to 2 or 3 decimals, just use your scientific or graphing calculator to do that. Just be careful when you put it in that you're in the correct mode. These would be in degree mode because you're given an angle in degrees. Again, another thing you might or might not know already, but if you know it, you'll catch my drift. The last of the problems for us, the fourth one, is going to be sort of the final challenger. It's not really the final challenger. It's actually probably the first thing you learned about right triangles, and that is that this question, involves the Pythagorean theorem. So the Pythagorean theorem, if you'll recall, especially if you skipped the key ideas section, the Pythagorean theorem involves the 3 side lengths of a right triangle, the 2 legs and the hypotenuse, and it says the sum of the squares of the 2 shorter legs is equal to the square of the hypotenuse. So obviously we have specific values in here, but this is going to be our process to find x, is to relate 7 and 9 to that x. So just before we do anything else, let's start right there. Based on this triangle, x squared plus 7 squared is equal to 9 squared. And simplifying this out a little bit, that's x squared plus 49 is equal to 81. And then from here I can solve this a little bit further. X squared will be equal to 81 minus 49. And let's think about that as like 81 minus 50 is 31, but there's an extra 1 there, so x squared equals 32. Last but not least, we'll solve for x by square rooting both sides. We don't need a plus or a minus here because we're assuming that this is an actual real triangle, in which case there are no negative sides, although keep in mind later in honors pre-calculus that will be a thing. And basically we'll get that x is equal to the square root of 32. That is an acceptable final answer, except that you can break this down a little bit further. Keep in mind the square root of 32 is the same thing as the square root of 16 times 2, which is the same thing as 4 square root of 2. So if you did want to simplify this completely there, and it does say answer should be in simplified form, that might be what your teacher is talking about here. So I'll write both of them here. You'll have to consult your specific teacher to know whether one version is acceptable over the other. But there is our first answer. We've got our x. So now if you're not careful or not paying close attention, you might think that this problem's just done. We solved for x, but there's just no y. Hooray for us. But there is one more variable that we haven't addressed yet, and that is the angle theta. On all the other problems, we were given enough information to know all of the angles right off the bat in these right triangles. Here, though, we only know it's a right triangle. We don't know what either of the angles is. Now, as I've mentioned, without a calculator, we're not going to be able to get the a specific approximate value, like a decimal version here, but we can establish what it is exactly by using the given ratios. So what I'm going to do is I'm going to go back in here one more time and look at the information we have and then set up a trig ratio that connects them together before finishing the problem. So relative to this angle, we have the opposite side and the hypotenuse. So again, we're given the opposite and we're given the hypotenuse. Yes, we did actually find the adjacent side, but we had to find it, so I'm going to stick with the ones that were given for simplicity and to make sure that none of our mistakes from earlier compound themselves. So from here, if we have opposite and hypotenuse, that makes me think of sine of theta. We know sine of theta is opposite over hypotenuse, op over hype. And so basically for us, that's what I want to actually use here. I'm going to point out that the sine of theta is equal to opposite over hypotenuse. Now this doesn't answer our question because we don't have theta by itself. It's like we are trying to find those values of the missing sides or angles, so we need to get the angle by itself. Like our goal here should be to end up with, eventually, theta equals something. Well, in order to get there, we have to figure out a way to undo this sign, and there's a pretty simple way to do that. So just to kind of illustrate what it is as with everything sort of mathematical and in an equation, if we want to undo something, we need to use its inverse. So what we're going to do is we're going to sine inverse both sides here. Some places will call that arc sine as well. Again, varies by teacher and sort of by context, but they mean the same thing. But effectively, sine inverse of sine is going to be equal to theta, and then sine inverse of 7 over 9 is what? I don't know. It's sine inverse of 7 over 9. Give me a calculator and I'll tell you. For us, though, that's what we're looking for. That is our exact simplified version or simplified final answer. there it is. So theta would be sine inverse or arcsine. Again, if you know that terminology, you can use it. Sine inverse of 7 over 9. And again, if we put that into a scientific calculator or graphing calculator in degree mode, we would get the actual value out. But that's not what this question on the ESQ model is all about. It's just about establishing these relationships and showing that you can navigate all of the major relationships of right triangles, whether that's trigonometry, the special right triangle proportions, or in this particular case, the Pythagorean theorem, and again, some basic trig and inverse trig. And with that said, that actually brings to a close what I was going to talk about here. So just to kind of remind you sort of what we were looking at in question number 6, we were bringing together all the big right triangle relationships. We talked about them really briefly in the key ideas section, that there are some special right triangles, in particular the 30, 60, 90 and 45, 45, 90 triangles, the latter of which is called an isosceles right triangle because those two opposite sides are the same length. And those have sort of baked in or built in really nice proportions that allow us to use them really quickly. Beyond that, we talked about the 3 basic trig relationships, the trig ratios, sine, cosine, and tangent, and what their ratios were relative to a given angle. There are more out there, but these are the 3 you're expected to use on the ESQ in the first half of Honors Pre-Cal. Then last but not least, I just reminded you about the Pythagorean theorem, so that way you had that in the back of your head. And then our problems use that. The first one was 30, 60, 90, so we saw those proportions in action. The second one was a 45, 45, 90. This one's kind of cool because you really only need one proportion because either you're finding the same thing twice or you're given one and you can just match it right off the bat. Then we did one that involved just pure trig, and I kind of showed you a strategy to avoid sort of extra work. We just kind of set up those trig ratios and figured out which ones were workable and which ones weren't. And then last but not least, I used the Pythagorean theorem as well as inverse trig, actually, as it turned out, to establish nice expressions for the 2 missing sides here, including one that was an angle. So with that said, that completes what I'm going to be addressing in this particular video. So thank you for watching. I hope that you got some good insights so that you can nail this question. I think that there's a lot more variety in this question. It kind of reminds me of the factoring question just because there's so many different versions that you can run into. But at the same time, I think that they're pretty familiar fundamental skills. They're super important going forward in pre-calculus as well. So I think this is one that you can kind of nail down pretty effectively and get comfortable with. You just have to know a couple really foundational skills to do so. In any event, though, I hope this is a good tool to helping you sort of firm up those foundational skills. Yeah, thanks for watching and have a good rest of your day. See you in video number 7, I'm sure.